Hey, all right, so this is a continuation of section 5.6. We're going to be doing one more example of graphing rational functions and also talking about the rule for figuring out if you have a horizontal or an oblique asymptote. And there's actually a nice classification. So say we have f of x equals, so it's a rational function, p of x over q of x, where these two are polynomials. We'll say that the degree of p, the degree of q equals n for one, m for the other. And from the polynomial section, we know how to find the degree pretty quickly. All right, so it turns out that we can actually figure out if we have a horizontal or an oblique asymptote by solely looking at the 2 degrees. And actually by looking at the 2 degrees, we can actually get a pretty good idea of what it is. Okay, so what we're going to do is just sketch a little table. So we do if. So if the degree on top, so the degree of p is less than, strictly less than the degree on the bottom, then we get a horizontal asymptote at 0. The idea for this is that the bottom is growing so much faster than the top that the function just gets sent down to 0. If n equals m, then we have a horizontal asymptote at, and this is where we need to write a little bit more information about our polynomials. We'll say an is leading coefficient of p, bn is leading coefficient of q, then we get a horizontal asymptote at the leading coefficients. I guess that should be bm at an over bm. So all we get when the degrees are the same, all we have to do is look at the leading coefficients and we can figure out exactly where the horizontal asymptote is. And then if n is greater than m, then we get an oblique asymptote. And we find it through polynomial division. So we've seen examples of all three of these in previous graphs. So for the second one, n equals m, that was the case where they're growing at about the same rate. So our example was x divided by x plus 1. And in a sense, x and x plus 1 are growing at the same sense that they get close to each other. If it was x divided by 2x plus 1, that implies a horizontal asymptote at 1/2, because we can think of that the bottom is twice as great as the top. So the asymptote has to be at 1/2. And if we have an oblique asymptote, then all we're doing is just using polynomial division to find the oblique asymptote. And it actually looks like, it'll always look like a polynomial of degree n minus m. So in the case where the n is just 1 bigger than m, so like x squared divided by x plus 1, it looked like a polynomial of degree 1, so a straight line. But if it was like x to the 4th divided by x squared plus 1, then it would look like a quadratic on both sides. And we'll look at some examples of that in class. All right. So the last thing that I want to do is just show an example of why we don't always have a vertical asymptote. Try and see if you can think of a rational function that doesn't have a vertical asymptote. All right, so there's two answers. So the first one is if it's a polynomial. That's kind of the cheap answer. That's not that interesting. We know how to graph polynomials. We know they don't have vertical asymptotes. And it's just by the way we wanted to define our definition where we also made them rational functions. The second is if the denominator is never 0. So for example, you could have f of x equals x over x squared plus 1. In which case, our function is going to look something like this. Draw a graph. The only place where something interesting happens is 0. That's our y-intercept. It's also our root. X squared plus 1 is never 0. So we don't have any place in the domain where it's not defined. So the only time it can change sign is at 0, because that's where we have a root, and we can only change signs at roots or asymptotes. So we plug in a positive. We check f of 1, and we get 1 divided by 2, which is some positive number. And because x is odd degree, we know that it has to cross through. So on the other side, on the negative side, it's always going to be negative. And then by our rule above, we know that x, the degree of x is 1. That's degree 1. The degree on that is degree 2. And so since 1 is smaller than 2, it's going to have a horizontal asymptote at 0. So it actually ends up just looking something like it shoots up and then comes right back down. Shoots up. And then it starts to approach 0. And that's what this function looks like. And maybe you're thinking, Weston, how did you know there were humps there? Well, I've gone ahead and taken some calculus. And in calculus, you'll look at this function and find where those peaks have to be. Or you can just plug in numbers yourself and see that it would have to have something whose shape looks like this. The other way to think about it is that when it's coming out of this 0, it's becoming positive, and then it has to get close to 0. It has to approach 0. So at some point, it was some number bigger than 0, and then it's getting closer to 0. So it'd have to have some shape like this. All right. Well, that's it for videos on graphing rational functions. I hope that cleared up a lot of possible confusion. I know there's a lot of different cases, so this is a good section to try and just be intentional and organized with understanding how these functions work.